So for thermal concepts, we again have the same situation where in the entrance region of a duct, we're going to have the growth of a boundary layer. We have a temperature difference between the surface of the duct, let's say, and the flow of the fluid. So in external flow, we called that temperature difference Ts minus T infinity. In a duct, we have to be a little bit careful though, because as we move through the duct, we might be changing the mean temperature or the bulk temperature. So we're going to, in internal flow for thermal considerations, start talking about Ts minus Tm, right? Where Tm is actually something that we're going to have to solve for in a lot of cases. So here, right, we have our thermal boundary layer that's growing. If it's laminar, we see that in this situation, the thermal boundary layer is going to meet at this X fully developed. And then at that point, we have internal flow. And for this, now it's the local heat transfer coefficient that remains constant. Before we said shear stress remains constant for thermal, it's local heat transfer coefficient. So if I, let's say, have a very long pipe and I'm well away from the entrance region, I can solve once for my local heat transfer coefficient, and it's going to be constant, right? That local is going to be constant through the entire pipe, aside from the entrance region. Okay. So let's sketch the temperature profiles internally here. This is about as far as we'll get today. So here's our duct. Okay, so let's pick a few locations and draw this, the temperature profile. So we have coming in, so we have coming in our boundary layer, it's growing. The boundary layer is growing. Eventually it meets in the middle. And then it's like this. So let's draw the temperature profile at here in the developing region, here at the fully developed point, and then downstream of the fully developed point. So my temperature here, let's say this is Ts. This here is T infinity. Right? So this temperature profile is going to look something like this. So in the internal region, we have part of the flow that hasn't been disturbed at all. And coming in here is our T infinity. So that kind of makes sense. We're right at the wall. We have our laminar boundary layers growing. As we move on, then we have, again, Ts here. So Ts here. Now the boundary layer is fully developed. It's all the way up to the midpoint here. So that's going to just look like this. It's this parabolic shape. And that's fine. So now we have right at that point where it's converging, the fluid right at the middle of that is still at T infinity. Right, so this all being T infinity coming in here. Now this is T infinity. So what happens though as we go further along, right, in X? It's not that this temperature profile becomes fully developed. It doesn't. We actually continue to add heat and up to the point where the entire flow is going to be at Ts if Ts is held constant. And so this is assuming a constant T sub S. So this is now going to look like, okay, so this would be Ts here. You move far enough down and we're going to see something like this, where this is again T infinity. This point here is Tm, and Tm is greater than T infinity. So you're moving along, and eventually we're going to converge this whole solution to a constant T sub S if we go far enough. So that's the constant temperature case. Could maybe plot out temperature as a function of position here. So if we looked at so T, so let's call this Ts. Let's call this T infinity, and this is my position X. So if I held Ts constant here. This is Ts. What would my mean temperature, that's like the integral of the temperature over all positions, what's my mean temperature going to look like? Well, it'd start off at T infinity, and it would just sort of converge like this. So eventually, as we go far enough, that mean temperature is going to approach Ts.